See, and it extends out. And as it gets bigger and bigger, these are just the patches. The patch ends up being small, and the patch gets bigger and bigger and bigger because the sphere gets bigger and bigger and bigger. Think of your mouth right here, right? You're facing towards me, my hand, right? You have a balloon. It's got just enough air in it so that it's not deflated, but you can tell it's not blown up at all, any way, shape, or form. You know what I mean? And it sticks out to here. Then you put a little square little area of magic marker onto the balloon. And then you start blowing it up. The bigger, it's going to get bigger and bigger and bigger. But as it gets bigger and bigger, right, the thing that you drew on there, the square you drew on there, is going to get bigger and bigger too. And you blow it up even more and more and more because you're expanding it. You're making it big. You know what I mean? So the square that you drew will get bigger and bigger and bigger and bigger and bigger and bigger, just like it's doing here, right? This is a patch from the sphere. Each one of these and this patch and this patch and this patch and this patch is the same patch, right? It's just the sphere expanded everything. You know, you can see this is the expansion right here. These red lines. But I want you to understand and see too that the further, if this is Earth, right, just like with the light rays, you only have all these photons go on this, you know, little patch here, right? Now the patch is 4 times bigger. So that means those photons have to spread out over 4 times the area. You're going to be 4 times dimmer, right? Just like over here. Now it's 9 times the space. These photons have to spread out on this 9 times more space. So it's going to be 1/9 the brightness, you know what I mean? And etc., etc. But this goes on for gravity too. See, these squares represent the gravity that you feel at that space and time, you know what I mean? And there's a sphere that goes all the way around the planet, and this is just a patch of it, right? But the patch gets bigger and bigger and bigger. And why does the patch get bigger? Because the energy, you know, that forces gravity, that gets smaller and smaller. It has to be distributed over more and more of an area, right? So the energy or the force or anything has to be distributed more. That means you get less per little square box, right? Here you got 16 little square boxes. On here you only had 1. That gravity has to be distributed over all this area, right? So you only get 1/16 of the gravity here than you do there, all right? And remember, gravity is a force. We just say it isn't a force because it doesn't affect baryonic matter. No objects, people, ships, balls, doesn't affect none of that, okay? It only affects space-time. It accelerates space-time down at the surface, 9.8 meters per second squared. And then it gets less and less and less and less and less and less and less, right? As it goes away from the planet, that gravitational force, pull, it gets weaker and weaker and weaker by this inverse squared law, right? So you understand that, you know, each one of these, you know, if you start out here and you have a little space, each time you come out, you're going to spread out your light, your whatever, your energy, your force, whatever you're talking about, your gravity. You're going to have to smear it over the entire surface. So you're going to have less and less and less of it. You know what I mean? That's why you have less gravity up here, because it's smeared over, you know, bigger area, whatever, space. And why you fall less fast, right? It's because the space hasn't been bent or curved. Down here you got a lot of curvature. Up here you have little curvature. You can see over here it barely has any, because you can see the acceleration. These lines, the path goes this much, that much. Now look, next hour it goes this much. This now the third eye, it's even more. It's accelerating down towards the Earth, right? This ball. You can see there's barely any curvature. This first, the further away you get from the planet, the less you have curvature. This is what they mean. See how there's barely curvature here, but here it's almost straight up and down. Especially like once you get up to this point here, right? It's almost going straight up and down, right? Because you're moving faster. Well, space-time is, you know what I mean? If you're floating there, you'll go along with space-time, just like if you're in a river, you know what I mean? You just go with the flow. And this is, I told it many times, this is a mathematical thing where the paths are accelerated, not you, the paths are accelerated. But it's really actually the space-time that's being accelerated. Now I want you to think about it. If you have, this grid is space-time, right? And it's being accelerated down to the planet, right? What happens? What do I always say? It shrinks. Hey, look at this. It shrinks. Look at the space-time. It used to be this big. Now it's shrunk down to there. Now that's it's being and look how it's accelerated. That's what your weights are being accelerated down, right? First you're losing 75 pounds between 125 pounds. That's a lot. But look on the next jump. When you go another distance, 4,000 feet, which is from the center of the Earth to the ground, right? That'd be 4,008. Now we're at 12,000 feet, right? What do you look at the difference? It's only like what? 14 pound difference, right? Over here it was a 75 pound. Then it goes. It's only a 14 pound difference. Over here, it's only a pound, 1.2 pounds. See, your weight loss has been accelerated down because space-time is accelerated this way, right? So from this grid to go from here to here, right? It's slow, but when it gets from here to here, the curvature gets to here. Now the curvature is more. You can see the curvature is more. So it accelerates. That's what the acceleration is. So from getting to here, it takes a while, but from getting to here it takes less time. Getting from here to here takes less time. Getting from here to here takes less time. You can see it's accelerated, right? But you can see that also that the grid is shrinking. It's smaller. And not only is it gets smaller, it's going to. You can see right here, if this was a ball, it stays on the same spatial coordinates. If this was spatial coordinates E is following the ball. It's not the ball that's accelerating down, it's the space-time accelerating down. Okay? The ball's is floating there. It's just like if you picked up a cup of water and there was a goldfish in it. You picked the fish up and you moved it over to the other side of the counter. Okay? The fish really never moved relative to the water, okay? Just like the ball. The ball isn't moving, okay? It's just the water or the space-time is being accelerated down to the Earth. It's being this is everything to the right here is the time thing. We wouldn't see that. We would just see the ball accelerating down. We wouldn't see this curvature. But we can see with the graph there's curvature, right? But in real life we can't see it. We would see this ball accelerating downward. And the more it got closer to the Earth, the faster it accelerates. More acceleration. More curvature, because that's how geodesics works. You get more curvature at the end. But remember, this is an actual sphere, right, that goes all the way around the Earth. Same way with this, and the same way with that. What happens if the space-time is this big, just like a balloon? When a balloon deflates, what happens to that material? It shrinks. It gets smaller. Yeah, that's what happens with space-time. It shrinks. It gets smaller. I mean, technically, it expands on both sides, but it's accelerated downward and then disappears. Okay, and since it disappears, this space-time goes. All the space-time ends up down in the center of the Earth, disappearing. You might as well say it's shrinking. You might as well say it's, at that point. The last thing I wanted to say was, when it moves out, I want you to notice a pattern. They put you put an L on it. See how this, if you cover up that one thing, now if you cover up these four things, there's another L. If you cover up these, it's just adding on an L. It's adding on to the length and it's adding on to the width. So you end up with a letter L surrounding what was already there. You know what I mean? But you'll see, not only does the space-time accelerate down, right, to where it shrinks this way, it shrinks this way too. It shrinks in every way. Even though it's getting expanded. So anyways, we're going to get on to the next video, and we're going to talk about, right, what, you know, I always say that the Earth's ground is accelerating up. We're going to talk about the exact speed, because it doesn't really accelerate, it just goes at a certain speed, okay? It's the space-time that's accelerating, and it all just depends on relativity. You know, you can say because of relativity that in one frame of reference, that the Earth's ground is accelerating up, okay? But is it really accelerating up? No, not from any other frame of reference, okay? But the space-time is moving at a specific velocity at the point of the ground, its surface, you know what I mean? It's moving at an exact velocity, just like all these thingies. Space-time is moving at an exact velocity, okay? But at each point, it's accelerating up, right? Like on the surface of the Earth, it's moving at 9.8 meters per second, right? But over here, let's say it's, you know, this would be the ground, 9.8 meters per second. Up here, say this is 7 meters per second, you know what I mean? And this is 5 and this is 3. But when this gets to here, it's at 5. And when this 5 gets to here, it's at 7. And when this 7 gets to here, it's at 9. Each spot has an exact velocity of the space-time. It's just each time you move in, you know, the closer you get in, that velocity changes. So my point would be is if you're standing on Earth, all the space-time is moving through you at 9.8 meters per second, okay? It doesn't accelerate through you. It moves at a constant velocity through you, even though it's accelerating through space. But you aren't this giant. If you were this tall, then yeah, okay. But you aren't that tall, okay? So it doesn't accelerate through you. It passes at a constant velocity through you, okay? This is John Black, Super Chemist. This is not an instructional video. It is just a vlog showing a video account of some chemistry experiments I have done or am learning about. I do not go over all safety concerns, so if you repeat anything in the video, you do it at your own risk. This is John Black, Super Chemist. We got over 3 ounces of gun cotton here. Almost a quarter pound. Anyways, I strapped that gun cotton onto this shirt so like it's a shirt on a shirt.